All right, and we are up to our last video for topic 2. Super exciting. This video is actually really better used as just a review, but it does highlight one good point that we didn't really cover throughout the rest of the unit. Besides at the very beginning, it's maybe a good end because it brings us back to the beginning of the cycle. So on our very first day of this unit, we learned about tangent lines and secant lines. And then the next day, we learned about how to actually find a derivative, except you didn't have any of your fancy rules, no power rule, product rule, quotient rule. The only rule you had was the actual definition of the derivative. We learned that to take a derivative, you actually had to use this limit, evaluate everything. It was a whole bunch of steps. It was a lot of work. It's a really kind of arduous and tedious assignment. But once you finished simplifying everything, it would find the derivative. Now, because we've learned all of our rules, we can actually shortcut this and come up with an answer hopefully much faster with much less work. The only trouble is actually identifying what the problem is asking. And really it's being able to distinguish between, does this limit mean a derivative, or is this limit just a limit? And that's what hopefully this assignment is going to take you through. The first 2 pages are all going to be derivatives. This first page is going to have you take the derivative using this limit notation, but we're not actually going to use the limit notation to take the derivative. We're just going to recognize the notation and say, no, I know a faster way. So what do I mean here? Well, let's go through it. If you see this exact limit formula, then you need to be able to recognize 2 things about it. First, that f of x is the function being subtracted at the end. It's not the part with the h. So you need to be able to recognize f of x. And you need to realize that if you actually evaluated this entire equation, the result would be equivalent to f prime of x. But why do all of that if we know our derivative rules? If you can identify f of x and then just take the derivative with one simple rule, is there any reason to involve the limit? And no, there's not. Now, we might have to go one step further. We might be given a limit that instead of having x in it, actually has a value, and I'm using a to represent an actual value or a constant. Well, we're still going to be able to recognize 3 things. First, we need to be able to recognize the original function f of x, which is this piece at the end, but with x plugged in instead of a. Then we need to realize that what this entire limit is finding for us is actually f prime at a. It's the original function with the derivative taken and then evaluating that derivative at a. But we have a faster way to do it. We just start with the function, we use our derivative rule, and then we just plug in a. So what does this look like in application? Well, let's take a look at this limit down here. This limit fits the form of f of x plus h minus f of x divided by h. And we need to be able to recognize that the function at the end is x squared. And this limit is really asking us to find what is f prime of x. Well, I'm not going to use the limit to do that. I know how to find the derivative of x squared. The derivative of x squared is just 2x, and so we're done. Notice that x is plugged in, so we don't need to use this last column. We're not finding the derivative at a point here. So let's take a peek at our next one. Our next one is this limit without an x, which means to me that they've replaced the x with a value. Now this does not mean, and I'm going to erase this, this does not mean that f of x equals 1 to the 4th. No, that's not the function, right? They've replaced x with a value. So it might help you to think of what would this look like if x was plugged in for that constant, right? And that constant you can see inside the parentheses. This is the function on the outside. Well, this is going to let us see that our function is x to the 4th. Well, what is this limit actually trying to find? This limit is trying to find at the very end f prime of 1 because they've replaced x with 1. So if this is trying to find f prime of 1, how do I get there starting at f of x? Well, we take the derivative. That is, of course, 4x cubed. And then to find f prime of 1, we just substitute in 1. 4 times 1 cubed, which is 4. Easy. Now, again, you could go the really long way around. You could multiply out 1 plus h times itself 4 times, multiply all that out, subtract 1 to the 4th, factor out an h, plug in 0, simplify it down, and you would get 4. But why do that when we know our calculus derivative rules? So at this point, I'd say go ahead and pause this video and try the rest of this page. If you get stuck, you can unpause the video, and I actually have all the solutions to this written at the very end as well. But I think this is probably given enough to you. You can go through and you could figure out the rest of these. If you get stuck on any of them, it's either because A, you weren't quite sure what was happening, what the function was, or B, you just didn't realize what the function's derivative is. That might be the case right here, right? You're like, well, I know f of x is tangent of x, but how am I supposed to know the derivative? Well, you're supposed to know the derivative because you need to have all your trig derivatives memorized. That's secant squared of x. Try the rest of this page, check your solutions on Teams, and then whenever you're ready, unpause and we'll move to the second page. Alright, our second page is very similar to the first, except now we're going to look at another limit definition of the derivative. It is also a valid way to find derivatives if we take the limit as x approaches c and do f of x minus f of c divided by x minus c. And if we simplify all that down, you're going to find f prime of x, or in this case, f prime of c. This one's always going to find a derivative at a point. Why don't we use this one too often? Well, unless it's something like this first one where you can factor the top and simplify, it turns out that simplifying a lot of these is a lot trickier just because you have fewer terms, you don't have the h to try and work with. It's pretty darn tough. So we can still use this the same way. We need to recognize f of x is going to be at the beginning, and that this is eventually going to find f prime of c. So how do we get there? We take the derivative with respect to x, and then we plug in c. So let's take a look at one. Our function is going to be x squared. Okay? We eventually are trying to find f prime of what? Well, notice that the c value is actually 3 places, but I think it's going to be easier to see it in the denominator here. They're trying to find f prime of 5 as x approaches 5. So eventually, I want to be able to find f prime of 5. Okay, well, f prime of x is 2x. F prime of 5 is just 2 times 5, that is 10. Easy. Now, where do these problems show up? Honestly, they usually show up in the multiple choice non-calculator active. And they're really just trying to make sure you know the definition. So they're going to give you something that looks like this, and then they'll just give you 4 multiple choice answers and say which one matches. And you might freak out a little bit and be like, but I don't know how to solve this limit. You're not doing a limit. You're just recognizing that the limit means do a derivative, and then you're bringing your full calculus brain to bear, and you're doing the derivative. Once again, try this page. If you get stuck, the worked out solutions are on Teams at the end of this file. At this point, you should have finished the first 2 pages. You do need to realize that there is a third definition of the derivative, and we briefly talked about it a while back too. It's known as the symmetric definition of the derivative. It's actually what most calculators use to find the derivative at a point. And it's given below here. I would say that it's probably something you should memorize, right? You need to recognize it. However, I actually haven't seen it show up on any AP exam ever. So they say you need it, but maybe it's less important. I'm still going to quiz you a little bit on it for this review. Well, what does that mean? It means if you see this exact format that you're looking for f prime of x, and if you see this exact format, so no x in here but a, it means you're looking for f prime of a. Alright, well, the second half of today is some fun practice and or review. And a lot of this is actually going to come from Unit 1, from Topic 1 back to limits. Because in Topic 1, we learned about limits and had no idea what derivatives were. And we need to still remember that limits don't always mean the derivative. In fact, there are very few limits that mean the derivative. Let's take a look at this first one, right? The limit as x approaches 2. Well, that's not a derivative. It doesn't fit the f of x minus f of a over x minus a. There's an x squared. It doesn't have any h's in it, so it's not our first definition or the symmetric definition. That's just a limit. It has nothing to do with slope, and we still need to be able to take limits for this course. That's one of our big ideas. Well, how do we take the limit? You might go the wrong way here, and you might try to factor x minus 2x plus 2, but then hopefully you'd realize the denominator doesn't factor with real numbers. It's not x plus 2 times x plus 2. Multiply it out. So you're like, oh no, what do? I can't simplify. But you've forgotten the first rule of limits. The first rule of limits is try direct substitution, right? When we try direct substitution, it just becomes 2 squared minus 4 divided by 2 squared plus 4. 4 minus 4 over 4 plus 4. This is 0 divided by 8, which is 0. This means on this complicated looking graph, as the x approaches 2, the y's approach 0. However, as we get to our second one, we need to realize that this matches our symmetric definition of the derivative, and this is a fancy way to say, find f prime of x. Okay, well, f prime of x, I think the first thing we're going to have to do is identify what is f of x. Well, f of x is, here's x, here's the function that's acting on it. I think f of x is just the cube root of x, or x to the 1/3. And you can tell because if you do f of x plus h, right, and apply that here, then x plus h gets plugged in for x, and we end up with this piece up here. Okay, looking pretty good so far. We have to find the derivative. This is 1/3 x subtract 1 to the negative 2/3, and I think that's it. We were just looking for f prime of x. You could clean this up, right? 1/3 times 1 divided by x to the 2/3, or 1 divided by 3 times the cube root of x squared, right? Any of those are fine. But really, that's all there is to it. So the rest of this is really you determining, are you doing a derivative, or is it just a straight limit? Derivative, limit, derivative, limit. How do we get through it? I again have all of this worked out for you on the last couple pages. You can see all the worked out solutions here, or you can see that this just isn't going to load and it's going to sit here and look strange, which is fine. But on Teams it is all loaded and good to go. However, there is one problem I wanted to work through, and this is problem 5 right here. Problem 5 is gnarly. We did one of these at the very beginning when we did some limit properties, but I figured it'd be fun to go through again. This is very atypical, not typical of limit questions, but it did come up a couple years ago, so it's probably a good one to remind you of. So it says the graphs of functions f and g are shown in the figures above. Which of the following statements is false and why? Let's just go through each of them. The limit as x approaches 1 of f of x is 0. So as we approach 1 from both sides, are the y's approaching 0? Yeah, definitely. They're approaching 0 here. This is true, so I'm going to get rid of it because it's true. We're trying false. The limit as x approaches 2 of g of x does not exist. So as we approach from both sides, oh yeah, that's a jump discontinuity. The one-sided limits are in 2 different spots. That's also true. The limit as x approaches 1 of f of x times g of x plus 1 does not exist. And here's where things get weird. Okay, a couple ways to think about this. I'll probably have to erase a few times. The limit as x approaches 1 of f of x times g of x plus 1. Well, the first thing that we don't want to do is we don't want to plug 1 in here. And the reason we don't want to plug 1 in is because we don't know if those functions are continuous. If the function is continuous, then the limit value equals the value of that x value plugged in. Well, we know this one's not continuous. What about g of x plus 1? Is that continuous? Well, actually, I don't even see the graph of g of x plus 1, and I know it's going to come in handy. So I'm actually going to create the graph of g of x plus 1, and I'll do this off on the side. I know I have extra paper that you guys don't have, but you can just watch and be amazed, or write it on a separate sheet. So this is going to be the graph of g of x plus 1. And the way that I'm going to create this is to remember that we can translate or shift functions based on our h and our k. H is a horizontal shift, and since it looks like 1, that means they're actually shifting everything left 1. So they're going to take this whole graph, and they're going to shift every point to the left 1. And same thing, they're going to take all this and shift it to the left 1. I think visually you can probably see where this ends up. I don't need to show too much work here. They're going to take this point, which is at 2, shift it left 1 to 1, so that's going to be right here, and then it just goes out this way, right? And this is 1. And then they're going to do the same thing here. They're going to take this, shift it left 1, so now it's down here, and then that should be an open circle, apologies, and then it goes that way. And this is, of course, -1. All right, so there's the graph of g of x plus 1. And that graph's also not continuous at 1, so I certainly can't plug 1 in there either. Well, the next thing you might want to try, and you wouldn't be faulted for thinking this, is you might say, well, let's just split this graph. Let's define the limit as x approaches 1 of f of x, and then multiply it by the limit as x approaches 1 of g of x plus 1. Well, the limit as x approaches 1 of f of x we found earlier. That is 0. But the limit as x approaches 1 of g of x plus 1, take a look at this, as we approach 1 from each side here, that does not exist. That's a jump discontinuity. And you're like, oh, okay, 0 times does not exist, gotta be does not exist. We're done with it, seems true. But it's not, because we made a false step here. And the false step is we are only allowed to look at the limits as separate entities if both of the limits exist. And as soon as one of them doesn't exist, we are not allowed to do this step. So you're like, okay, but how do I actually find the limit then? Well, the way we find the limit is we find the limit of this graph. This is a single graph. And you're like, no, it's two graphs. I see them up there, two different ones. Oh no, we're going to make one single graph. We are going to create the graph of all the f of x values multiplied by all of the g of x plus 1 values. So what does that look like? Well, I'm going to draw another graph. Okay, it looks something like this. And we're going to multiply f of x, all of these y values, which seems daunting, against all of these. Now looking at g of x plus 1, the y values are actually very easy. The y values at the top are just 1, so let's start with that. If I take all of these y values starting at an x of 1 and moving left, let's see what that looks like over here. Moving left but including an x of 1, I'm going to multiply all of those by a y value of 1. Well, if you multiply this by 1, it's just the exact same graph. So here is 1, here is 2, here is this. We'll maybe leave an open circle, closed circle at 2 because we multiply by 1, and then this guy goes something like that. I multiplied them by 1, so the graph didn't change. However, the part that will change, I think, is this second part. Notice now I'm going to multiply everything by negative 1. And when we multiply all this by negative 1, it's going to switch the sign. So my new graph is going to pop up like so. This is the graph, the super graph, of f of x times g of x plus 1. So can we find this limit now? I think we actually can. We can just look at the graph. The limit as x approaches 1. This is 1 right here, by the way. The limit as x approaches 1 from both sides. This actually equals 0. It equals a number. So this limit doesn't not exist. So this is false, which means it is our actual answer. And you could create this graph as well and find the limit there, and you'll see that it does exist, but C is our false one, so we're going to stop there. The rest of these aren't too terrible, and I think from my worked out solutions you'll be able to get through it no problem. If there are any really tricky ones, email me, set up a meeting, whatever works best for you. But hey, you guys are done with our longest unit for this semester, so congratulations on getting through it. We'll have a few days of review, but this is really the time where you want to buckle down, take that back page of your textbook or the formula sheet we'll get next class and really start memorizing. You're going to use these derivative rules over and over and over and over again. And if you have gaps in your memory, it's going to make the next few units, really the rest of the year, pretty darn tough. This is the unit where you need to have things memorized. You can skip small stuff here and there. You can't skip derivative rules. It is the basis of our class. Thank you again for working so hard. I do appreciate each and every one of you, and I'm excited to see you the next time that I do see you.